So, thank you very much, Jean-Paul, first for presenting this jury, and for all the members of the jury to come today. Thank you very much. I also would like to thank the reviewers who took the heavy duty of reading this lengthy manuscript. Thank you very much. And also thank you for all people who have come, and some of them who have come from far away. So, I will start the defense of my habilitation entitled Vision-Based Motion Generation for Humanoid Robots. So, I will first give you a brief introduction of my biosketch. So I did my PhD in Japan, Tsukuba, and I worked on this robot, the Jack robot. His acronym means Just Another Clever Kid. And my main duty on that was to develop the distributed system to program this robot and implement a visual attention system. Then I've took an assistant professor position in University of Paris 13. And in 2003, Philippe Coiffet proposed me to join the Joint Robotics Laboratory, who is currently headed by Abderrahman. And I worked during this time on the humanoid robot HRP2. And due to the big earthquake of 2011, I've joined last in the Gepetto team. So the motivation of this work is the following one. It's to generate motion for complex sensory-based behavior for two kinds of application. Service robotics. So here, for instance, you have the Asimo humanoid robots who is able to autonomously bring coffee to people. Here, in a more industrial setup, HRP3 able to screw parts on a bridge. Here, in Akawana Industry, who is also the builder of HRP2, HRP3, and HRP4, here, who is a robot designed for entertainment. The other class of application is rescue robotic in a very scattered environment in the context of the new DARPA Grand Challenge or in the battlefield. Here you have the battlefield extraction robot who is able to pump 100 kilograms in a dynamical stable position here. So in this class of robot, the difficulties we have to cope with are the following ones. We have first to plan trajectory and task. Task means control. To be able to cope with the balance problem, we don't want the robot to fall in this scattered environment displayed here, for example, by the University of Washington using the UBO robot. So it's a mixture of simulation and real video, but show that the kind of application we want to tackle in scattered environment and one which are unstructured. And when we want to plan or generate motion, the main problem is to face the high dimensionality needed for this kind of robot. For instance, HRP2 or Asimo has 30 degrees of freedom to move and 30 degrees of freedom to manipulate, for instance, in the new setup of Asimo regarding the ends. So now, the question is what is the behavior? Okay, so we'll give a brief introduction based on game theory where we have two agents who actually play a game. We assume that we have a game score that we will call F, that the agent on which we are interested here is a robot, the HRP2 humanoid robot, and that this robot has a representation of the game, the environment of the game, and the other agent that we will call V, and that this agent can act in the environment, and the action will be here, for example, the position of the motors. Now, this game follows rules, which we will see, which will be precise later on, and gives rise to inequalities. And at the end, what we got is an optimization problem where we want to find a set of action which will minimize or maximize the game score, considering the representation of the environment, and the free variables of this problem is the action. So based on that, the problem is how can we build the cost function for the behavior of interest? I will give some proposal in the context of, for example, visual search on X-based view. How can we build an efficient world representation? and what are the constraints which are necessary, the one which are not meaningful and the one which are, and finally, how can we find a solution for this kind of problem? So, the main scientific question I've been trying to answer in this kind of setup, considering this kind of platform, is how can we break the complexity of the behaviors? Because most of them are NP hard. So during my, so what we can do as a first remark is that humans in their everyday life solve these kind of very hard problems. So during my PhD, we try to use this analogy of the humans and basically try to implement the human software, which is basically the connection of the neurons between each other, inside a classical computer, using new robot at this time, in 2000, humanoid robots for their richness of motion. Now the problem is that the complexity goes back into the simulation cost, so even if the software seems to be very powerful, the simulation on classical software is extremely costly, and moreover, due to the underlying computational model, it's very difficult to analyze. So then, during my assistant professor position, we worked on a different side, evaluating different kind of software in a standard platform, here the Habo robot, in a specific application, playing soccer. Now the problem is that when you try to build a very complex behavior, you need to build extremely big hierarchical finite state machine, which tend to be increasingly complex and which are extremely difficult to maintain. Moreover, because the Habo robot in this case had to be autonomous and has a very low CPU power, my main conclusion was the computation and decision autonomy on this specific step setup were too constraining. A very side work was actually to try a new model of computer. There is some open question in computational theory, which are maybe some analog computer may be more powerful. So we have tried to use a Schwa oscillator with nonlinear control as a software to drive a point robot from one starting position to the other. But the current problem is that they are even more difficult to analyze, and currently their capability is their applicability is quite limited. So, when I arrived in GRL, I took a very different approach to solve this problem, which was to find first an efficient practical formulation of the problem for our classical Turing machine and classical software system with a given robot, which is here, the HRP2 humanoid robot. We have also tried to use a general constraint on the robot to limit the search space, and instead of doing custom made solution, we have tried to build generic motion capabilities which are efficient and could be used in different kind of contexts on robot. And for what I will present, we almost forget the human analogy. So to be a bit more precise in the kind of application I've been trying to do, here we consider three kinds of the function f at a given time t1, which are this kind of form. And what happens is, depending on the information you take, the shape of the function change. And basically, for example, in this case, the global optimal switch from this position to the other one. And also due to other information or the state of the robot, you can have a slight drift or modification of the position of a local optimum. So for me, planning is the way of finding the new global optimum and the basin of attraction that are specified here, whereas control allows us to cope with the modification of the local minima position. So now to try to answer to these questions, for the necessary meaningful constraints, we will take into account the dynamics of the robot, the physical limits such as self-collision, joint limits, torque limits. We will take into account, which is very important for human and robot, balance. And other constraints, we will use tasks which will give us basic functionalities that we can put together in order to generate motion. Now, there is motion to deal with a huge source space. We'll use control and planning. And for the world representation, I've been working on self-localization and map building, object recognition, and tracking. So my contribution lies globally in 4 scientific fields: planning, computer vision, control, and balance. You can see that the journal paper I've published are scattered on these 4 fields, with a strong part on integration and validating this algorithm on the HRP2 platform. So, for those who had the chance to read my manuscript, there is several chapters. Unfortunately, because of lack of time and space, I will present only 4 parts, which are basically walking, whole body motion, visual search, and object model construction. So, let's now move on to computer vision and the next base view problem, which will give you an idea of how to build this cost function I was talking about. So here the problem is to have HRP2 building a visual representation of an object it doesn't know in an assumed known environment. So the robot here is facing this small house. The only thing he knows is that he has a small box representing the unknown, and what he wants to do is to find the next position which will maximize the unknown projected into his vision system under a set of physical constraints, respecting the joint limits. For example here, avoiding collision with the environment, avoiding self-collision, making sure that the feet are on the floor, it helps, and that the robot is, here in this specific case, statically stable. So for generating the pose of the robot, we build upon the work of Adrien Escan, who was a PhD student on this work, and Thorer Fouessot first tried to use this pose generator and try to maximize this cost. Now the problem is that this pose generator assumes that you have a C1 function, extremely smooth. But because we don't know what the robot has in front of him, we use a voxel map representation. We tried other things like Gaussian representation, but it induces, due to the discretization, local minima in the real function. And if you use algorithms such as FSQP, the algorithm will get stuck into local minima and will not converge toward the solution. So what we proposed is to use an algorithm proposed by Powell, which will build a convex approximation of the function and propose a local minima in this space, giving a trust region and a start pose. So we apply this due to some time constraints, this approach to only the 6D pose of the camera, position and orientation. Then when, for local region, we find the best position, we try to generate a pose which will take into account all the constraints, making sure, and if it's feasible, iterate around on these 2 optimization problem until we found a fixed point which will be the solution. It's going to be a local position, so on top of that, we do random search into the space where the robot is searching. So here you have the output, and you can see, as it is expected, that, for example, for this kind of small size object, 4 poses only are enough to rebuild the object which is seen here. And this is very much in correlation with the work of Claire Dune done at Lagadic, who show with Eric Marchand that if you build an ellipsoid approximation of your model, then you need only 4 points in order to see completely this ellipsoid. So the interest of this work, however, is that it's very generic, so you can extend it to more complex objects, which are non-convex. Here, for example, a small battleship mock-up, and the robot finds 6 positions without collision of the environment, which seems to be physically reasonable. You can even try to cope with bigger objects, and in the PhD of Thorea, we haven't shown that it can be used for buildings, for instance, or you can assume that you have a ship or a building that you want to explore, and that algorithm will work. Now, the other high-level behavior we have been worked on, and this time with François Saidi, is visual search. So this problem is, for example, trying to find your keys that you forget in your house. But this problem is quite difficult, actually. It has been shown to be NP complete by Tsousos in 1996. and which means that you need a heuristic strategy. You need to build again an approximation of the function you're trying to maximize. And because of the limited view, limited depth, and the fact that usually the robot, when he's trying to recognize an object, will depend upon the recognition and the lighting condition, we need active vision for this. So the rating function is quite complex, has a high dimensionality. So we proposed a way to formalize constraints in order to restrict the search space of the system. And for this, we introduced what we called the visibility map. The visibility map assumes that the robot, for instance, will have a vision system which has a Gaussian, for which the quality of recognition is modeled by the Gaussian. You have the minimum distance to see the object, the maximum distance. And from this, if you consider one voxel inside the environment, you have this region here, which is the intersection of the two spheres given by Hermine and Armax, where you know that you will see the best this voxel. So it's the first way of constraining the space. Now, in this specific case, we want the robot walk. So we know that in this current space setup, the height of the head will be constant. Then basically what we do is we do an intersection between the perception space and the kinematic space to get what we call the visibility map, and which is displayed here. So here you have a 3D reconstruction using stereo of the environment, and for each voxel, we project this sphere, intersect it with this plane, and what we have is this visibility map, where the most brightest point are the one where we will see most of, the bigger number of voxel inside the environment and in the best condition. So on top of this visibility map, we do maximum extraction. And this gives us the following video. So here you can see HRP2 exploring an environment. So the green part is unknown. The red part is the one which is reconstructed. And the blue one is in occlusion. So what you can see here is that the robot will get stuck for some time into this square. And the main reason is that to go over there, he has to go through this unknown part. He knows that he can step over some obstacle, but it's limited in time. So until he look at this part, the robot will continue to explore his environment because he knows that he has to increase his knowledge about this local environment. So here you have a snapshot of the real experiment. In this specific topic, we didn't use localization, so we are always correcting the position of the robot because there is some drift. And as you can see, it takes a lot of time. The overall behavior took 1 hour to be realized. And this work was a finalist for the Best Paper Award in ICAR in 2007. And so finally, you see that the robot is looking at the part who were forbidding him to go on the other side, and then he is now looking at the part which is occluded until he finds the object. So I will show quickly simulation. Well, everything is perfect in simulation, so it's much faster. In 10 shots, you will see that the robot is able to find the object, the purple one. And because of the distance, we ask the robot to find the object 3 times before converging. So with this approach, we almost didn't take into account the motion generation part. So it's very generic, it's autonomous, but it's extremely slow. So 1 hour for realizing the experiment is definitely not practical. So since then, I've been working on how we could use motion generation to speed up the realization of behavior. So I will consider on this part of the work the problem of motion constraint satisfaction problem. So there is not all the constraints here, but I think they are quite important, which means robot dynamics, the friction cone, which here is a general way of saying balance, torque limits, joint limits, self-collision, and collision with the environment. We could add impact or other constraint, but this is the one I will focus most on this part of the work. So now, for walking, we will consider a very low-dimensional way of specifying constraints for balance. So, as proposed by Pierre Brice in 2003, Pierre Brice-Weber, we can reorganize the whole dynamical equation to have at the top of the equation the other part of the mechanical system, which is here depends upon the acceleration of the center of mass, on which we project only the contact force through the Jacobian of the geometry of this contact point, and all the dynamics of all the bodies of the robot are projected into the derivative of the momentum. When you assume that you have just one contact, I mean, this gives us to the what is called the RMP model, which is also known as the inverted free wheel pendulum model, and give us to the rest of this problem is that can we find a trajectory for the center of mass and for the derivative of the angular momentum in order to have the contact forces here inside the cone of friction, making sure that the robot is balanced. So if we don't find such a trajectory, it's lost. We know that we cannot find a proposed motion. However, if we find such a trajectory, we also then have to solve a second problem, which is, can we, for the all constraints, find a motion which will not, which comply with the other part of the motion satisfaction, the motion constraint satisfaction problem. So the classical way of dealing with robots who are on flat floor is to use a center of pressure, where basically we take the set of equations I presented previously, and we have this generic form, which is a second order differential equation, which is still quite complex to solve in real time. So to solve this problem, what we generally do is assume that first the momentum derivative is equal to 0, and that the robot, the center of mass trajectory is on the horizontal plane. And you finally come up with a classical linear inverted pendulum proposed by Kajita in 1993. So the problems, once you have this very simple equation, is how can we find the center of mass trajectory given constraint on the center of pressure, which is a convex hull of the footsteps. So Kajita, in his very seminal paper in 2003, proposed to formulate this problem as a optimization problem, where basically you will minimize the difference between a reference trajectory, which will be the center of the footsteps, and the norm of the command. So there is previous work on this one, but this is the most well-known. Now the problem is with this system is that the center of pressure will have to follow this reference trajectory, and there is no guarantee that the solution will be in the support polygon. So then Pierre-Brice Vibert in 2006 proposed to constrain this the center of pressure to be inside a polytope, and show that we can expand this motion cost to other criteria, such as the one proposed previously. Now the interesting point is that with this formulation, your center of pressure becomes a degree of freedom. You can play on the center of pressure to minimize this cost function, which was not very the case in the previous formulation. Now, Pierre-Brice came to GRL to work with us during 2 years, and during this time, one of his postdocs worked on this formulation, used an off-the-shelf solver, and find out that when you try to solve this problem, when a constraint is activated, it's almost never deactivated. So we propose to generate a specific solver in order to find a solution of this problem. Now, using this particularity, we were able to decrease the computational time of a classical off-the-shelf solver, which is given here, and go up to 40 milliseconds for a classical problem on HRP2. Then, using this new formulation, we were able to go down to 8 milliseconds. But the control period for HRP2 is limited to this. So I did an implementation using warm start and limited time computation, which means that because we use a primal formulation of this problem, we always, during the iteration of the solver, had a feasible solution. And then what we did is just stop the iteration when we reach the 2 millisecond constraint. And what we found out is that the suboptimal solution is is not distinguishable from the optimal solution. So we've got almost the same quality with this solver than this one. So in the frame of national project I scientifically coordinated, we extend this approach and trying to find new cost function. And one of this seminal work was here to introduce a reference velocity of the center of mass. What is interesting then, your robot is not anymore a humanoid robot. You can send him reference velocity as a mobile robot. But it is constraint, so quite complex constraints. So the classical one I introduced previously. And the key point here was to add as a free variables footsteps. So now footsteps can be free. Can be changed and find by this optimization problem. But we had to find proper linear constraints. And the way to do that was done by integrating a planning approach. And I think that was a very interesting point of this work. We used an approximation and a learning of the feasibility footstep transition of the work of Nicolas Perrin that I will present later on during this presentation. So the next step of this work is that when we can specify a reference velocity is to use visual servoing to generate the reference velocity. So what we did here is take 4 desired images of the robot, such as this one, and ask the robot to minimize what he sees with the desired one and generate the motion automatically. The only things which is here specified by the user is the desired image, and everything is generated automatically. So for the tracking, we use Visp. And the reason why the robot is kind of slow is mostly because of vision, and vision on humanoid robot is hard. You can see the gap of vision we have. So Visp is quite robust. With all, all the perturbation we've got because of the walking, the impact, and the propagation of the impact through the mechanical structure, the precision of the tracking was kind of not so good, and we couldn't put the reference velocity speed too much directly inside the robot, so we filter it quite a lot, and this is why the robot seems to be doing these very small steps. So now let's go back to this general equation. In practice, the derivative of the angular momentum is not equal to 0. So how can we cope with that? Again, Kajita in 2003, this part is not that well known, but I think it's very important, proposed to use the preview control filter. I mean, the optimization problem I introduced previously has a filter. How can we use that? So you have the center of mass reference trajectory, which is the center of the footsteps. From this, using the preview control, you have center of mass trajectory. Using generalized inverse kinematics, you can get a whole trajectory for your robot. Using classical recursive Newton-Euler algorithm, you can then compute the center of pressure for the whole dynamic, what we call multi-body center of pressure. You do the difference with the reference trajectory, and you use a preview control on this difference of the center of pressure, and then have a difference of the center of mass trajectory. And this Newton-Raphson scheme happens to be extremely efficient. Only in 2 times you can modify the center of mass trajectory and the center of pressure trajectory by taking into account the constraints of the body dynamic of the robot. So it's a very efficient way to compensate the perturbation of the upper body imposed motion and use the center of pressure as a degree of freedom. So we use that with Bjorn Verels actually to do a breakthrough in stepping over obstacle with humanoid robots. So the previous work was here using quasi-static criteria. So the problem with quasi-static balance is that you constrain so much the position of the robot that he will always hit either the obstacle or self-collide. So what we propose here is to use a dynamical trajectory. And here, the heuristic is just to make sure that when you are in double support phase, which means that here, for example, when the robot is over the obstacle, that you don't have any kinematic constraint or you're not in collision. And if this happens to be true, then you know that you can generate the whole trajectory dynamically. So the only statistical position here is when the robot starts and ends. So now let's move on to the problem of when we have the center of mass trajectory, the whole body motion. So here it's a long joint work with Nicolas Mansart on a framework called the stack of tasks, which actually combine simple controllers together. And what we do for these simple controllers is we have few assumptions. We assume that we can compute a derivative. We impose that this error has an exponential decay. And most of the time, we define this function as the difference between the desired feature, as I've shown previously in the video with the structure which was followed, and the one which is currently measured. And what we worked on is a way to make sure that the task could be automatically combined together in order to collaborate mutually if that was meaningful, or exclude them if it's not the case. And this is fully automatic. So when somebody has worked on a simple controller, this system allows us to put them together in an automatic way. And the other interesting things I like about this approach, it's a kind of online optimization. It's like you solve the problems while really executing the motion. And the problem with that is basically, if you go to our local minima, you failed. And this is why planning is very important, is to make sure that when you are a basin of attraction, you are in a global maximum and that your robot is not failing. So this has been applied in the frame of a European project that our laboratory has been coordinated, and Abderrahman Kedar is at the heart of this project, who intends to put humanoid robot inside a collaborative working environment where the robot has to collaborate directly with a user and through a teleoperation. And in the frame of this project, I was in charge of the final demonstrator. So with the kind of basic controller we were using is, for example, here, the robot has 4 sensors at the wrist. So we did an impedance controller for the user to be able to gently move the robot. And what we recorded is a standard position of the footsteps regarding the position of the wrist. So the robot was always trying to find the footsteps which will go back to this standard position. So once we define these footsteps, we use our real-time walking pattern generator, combine them together with the stack of tasks in order to be able to generate a stable motion with a user to handle a table which is here up to 5 kilograms. So thanks to this scheme, we are able also to take the input of a remote teleoperator directly at the gaze level and the upper body. So now I will show you some excerpt of the video of the final demonstrator. You can see here our colleagues from TUM, the team of Martin Bus, who has a mobile, so the team has a mobile platform on which 2 7-degree force control arms are mounted. And the user is interacting with the end effector of these 2 arms. He has a head-mounted display here, on top of which there is a motion capture system, which gives the pose of this mounted display, which allows to control the head of the robot. And what the user here is doing by this driving this end effector are the 2 hands of the robot, and everything is generated online and in real time. So using the same scheme I showed, we are able now to, the teleoperator is able to grasp the handles of the table. We do switch between different tasks of controller using speech recognition provided by TUM. And then, using a different instance of the stack of tasks, we can switch to an autonomous mode where the robot is lifting a table with a user and then start to work. So the person will try to drive gently again using the wrist sensor of the robot HRP2 in order to reach this final position here. So the interesting part, the things interesting with this approach is that we tested it with colleagues from sociology, and we had 12 users who knew nothing about robotics, who never saw the robot, and they were able to guide the robot toward this kind of a setup. Not do the final task assembly I will show, but just putting the table. And on this 12 person, the average successful number of trials was 3, and almost, I think it was 3 who were able to do it directly. So which means that this is really practical. Also, it's quite slow. You can see again that the robot is going very slowly, and the main reason is the robot knows nothing about the future. He's making no assumption, so he's very conservative. He's assuming that always he will step, okay, and then suddenly somebody moves the hand, and then you say, okay, I have to move from 10 centimeters. The robot can go much, much faster than that. And again, the final assembly task. Again, just by simply playing on some of the gain of the here admittance control in some specific direction, here the rotation, the robot is gently following the person in a very complex setup. So, thanks to the stack of tasks, we're able to combine these simple controllers, integrate the priority with mutual exclusion using projection into null space. We're able to take into constraints with some recent extension that Nicolas has been doing, and also with at the dynamical level. Now the problem is that we still have some problem when the function we're trying to minimize have some rank deficiency. We can have speed discontinuities. We can get stuck into local minima, which I think is maybe one of the biggest problems. And when we switch between tasks, we may have some discontinuities. So this is why I worked after in the planning of this task. And for this, we tried to investigate the problem of footstep planning. So for this, when we started this work with Nicolas Perrin, the state-of-the-art method assumed that you know a discrete set of footsteps for which you have the whole trajectory, and you know that all the constraints I was talking about are fulfilled. And then you optimally plan in this subdimensional set of action to find a footstep. So it's very efficient. However, when you are in very constrained environment, you would like to be able to use other motion capability of the robot. And our goal has been to try to identify and learn this footsteps space. So for this, what we have done is we assume that we have a transition from one footstep to the other, which is a six-dimensional input space. Using all the mechanics I showed previously, we generate the whole motion on a limited time. We compute the distance to the constraints, and finally, taking the minimum of this distance to the constraints, we have a scalar value. So we learn the relationship between this input space to this output space. It took 11 days to do that with a lower dimensional version of this work. But the interesting point is when it is learned, when you just want to know what is this value given this input space, it takes 9 microseconds. So you can have a very aggressive planning strategy in order to plan actually all these controller I was talking about. And if you want to do that in real time, you are limited to 4 or 5 possibilities. So the approximation map, we were able to identify this shape. And what we did is fix inside the polytop, and you find the constraints on the footstep position I was talking about. So the application is the following one. Here you have HRP2 who is planning footsteps in a real time. So what we do is we have a lot of constraints. So the blue parts are the forbidden area. The robot, we change here the position of known objects, so we know the geometry, and the robot plans in real time the footsteps. So here it's not optimal. We want to have a feasible trajectory, and on top of that, locally, if we can, we try to maximize it. So here you can see that the goal can change in real time. You see that the system is doing a loop, and then he's going backward, and then we find a shortcut. And on the real robot, so here we can use them to step over some obstacle. Here we use motion capture because unfortunately, given we were not able to use the refinement of our planning system with vision, but we hope to cope with that presently. So, and what you can see here is that we move the chair and the system is permanently replanning and finding a new solution, even if we change the goal. So here you have a very simple setup where basically here you have the goal. On top of the helmet, somebody put a chair in front of the robot, whereas he's very close to the goal, but then he can find very quickly a new solution to replan. So of course it's not perfect, so you can see that the robot is slightly here colliding with the table. But it works. The problem here is that it doesn't have the model of the tripod inside the environment, so we have to remove it. So, the conclusion of this work on motion generation is the following one. It's possible at the control level to combine these basic controllers using the framework called the stack of tasks, but it has to be used with a planning framework in order to avoid local minima, which calls, however, for very powerful steering method, such as the approximation function I show. But we would like to go further. Indeed, I'm convinced that HRP2 has not been fully exploited. Abderrahman Kedar and other people in the world have shown that it's possible to do multi-contact motion with such kind of robot. Now the question is, can we do it real time, trying to minimize the kind of cost function I show? Can we do also motion generation using heavy object? We will change the dynamical property of the system, and can we go towards extreme motion? So now in this context, I will briefly explain my research project, which actually comes from a big frustration of the final demonstrator I show you. The robot was stepping, okay, because he has no knowledge of the task and what the user wanted to do. So what we would like to have is a model or a way to acquire a knowledge on the context and the environment to build what I call statistical oracles. And I think that for this we need awareness, make the robots, the humanoid robots, aware of its body, the context, and the environment. So, if we go back to this simple example, what we would like to have is to learn the transition of this global minimum based on this new information provided by the representation of the world, and use learning techniques actually to guess that the most probable next global minimum will be this one. Whereas to help the learning of the system, we want to have more powerful controllers and learn their domain of validity in order to speed up and cope with the dimensionality problem related with the learning of this kind of transition. So one of the work into this advanced controller, a very recent one, submitted to IROS 2003, is to go forward and integrate directly vision inside walking. So here we're not trying to minimize a reference velocity, but we use a preview control on the desired visual feature on the one, and we can integrate it directly at this level. So the other one is to actually get some feasible sequence of tasks to generate a complex motion. And the one we are trying to address with Nicolas Mansart while supervising the PhD of Sovarna Haak is to record humans and extract from their motion a set of controllers which is related to the humanoid robot. So it's not only a mapping problem between a human body and the body of the robot, but also the set of controllers that he's using. So the extension of the classical sensory motion loop here, where we usually take vision and plans where we want to see next the motion and then feed it back to the control, is the following one. We want to create intermediate statistical structure, such as the one proposed by Davison in 2009, which give us some higher representation of the world. Use a statistical ontology, which could be using information from internet. Then, when we, the first time, see a problem, use a classical motion planning problem, relate that with the control part to create a bootstrap between the intermediate statistical structure and the local optimization problem we want to face. So then, when the robot is facing a similar environment or situation he have seen previously, to not use the classical approach, refine the same solution, but go directly to the local, the most probable optimization problem. So the kind of challenge we would like to tackle with this approach is the following one. The Future Factory. So here you have the vision of Ford of Future Factory, which I think is shared with a lot of people in Europe and abroad, is to use a mannequin or the knowledge we have on this very structured environment, the fact that we can add additional sensor on this kind of setups, and with our interaction with some industrial, one of the biggest needs they had is to be able to handle real-life variability, which I think make very pertinent all the work I've presented previously. And in this frame, with a big industrial company in Toulouse, we are in the way of trying to build a proof of concept using this setup. The other challenge I think is extremely interesting and strongly pushed by Jean-Paul Lemont is to go towards extreme motion, such as the parkour, where, for example, we would like to have the robot jump. Well, actually, one day we made in Japan a HRP2 jump. It was not what we intended. The robot was able to cope with that. And so we know that there is some area where we could use this kind of robot. But it's very likely that we're going to break it. So one way of dealing with the complexity is to modify the mechanics to locally handle some very complex motion. For example, variable impedance, where IIT in Italy is a leading institute in this direction. But from the control viewpoint, what's the problem is that your system becomes highly nonlinear and you increase by 2 the number of unknown variables. So again, we need some way to speed up the resolution of the optimization problem related with the use of variable impedance robots. So for this, with colleagues from UK, University of Birmingham, University of Bristol, IIT, we submitted a FP7 project called the Triple E, that I'm the coordinator, who is trying to do this triple awareness I was talking about, where we want the robot to be aware of his control and physical limits, aware of the context, and aware of the purpose in order to decrease strongly the search space of the motion generation problem. We would like to apply this in a big industrial partner. As I mentioned previously, we are working on a proof of concept problem on that. We are also participating to one challenging project which aims at putting HRP2 robot outside, and it's sponsored by an international oil company. And finally, again in this kind of frames, we are involved in a proposal to propose robotics challenges to the robotic community. And finally, I would like to acknowledge all the students, my collaborators who helped me to realize all these works. Andrew Davison, Foslam, Abderrahman Kedar, who made a very nice environment at GRL, Florent Lamiro, Nicolas Mancer, and Pierre-Brice Wiber, who are the people with whom I'm working the most and with whom I'm continuously developing the idea presented here. Eiichi Yoshida, with whom I've been working quite a lot. Of course, the PhD student who made a tremendously work to make this happen. And all the collaboration I've been able to perform with postdoctoral fellows and project collaboration. And finally, I have a soft spot for the project we have been doing at Toulouse in the frame of this national project I was handling. So one day we had a proposal to make a artistic performance with a hip-hop dancer. And we were funded by the Mairie of Toulouse to do some show with this dancer. So he came here. We used a lot of our techniques we were developing with Nicolas to generate the motion. We did it in 3 months, whereas I think other people would have taken much, much longer. And we redid it. They like it very much. We had 700 people for the first time, and the second time the town hall of Toulouse come to us and ask to perform again, but this time without any security. And this is one of the longest performance we have been doing. I think this one, the first one was 20 minutes, and this one is 12 minutes. So thank you very much for your attention.